Welcome to Real Civil YouTube channel. In this video, I am going to explain how to calculate the design seismic force by static analysis method, that is equivalent static method, and we are going to use the latest code IS 1893 2025. So this code is updated in November 2025. So what are the changes? How to apply the clauses? For that, we will take one problem and then we will go on solving, and we will see the clauses given in IS 1893 2025. Also, I will cover the part of comparison of 2025 versus 2016 also. Okay. So let's start. If you don't know how to download the IS code, I have made the video. You can see in the description box the link, or you can click on I button. We need two codes basically: design earthquake hazard and criteria for earthquake resistant design of structure code of practice part 1, and design earthquake hazard and criteria for earthquake resistant design of structure code of practice part 5 building. Okay, the first one is general provision and part 5 is related to building, and we required both the codes. So let's begin. So this is the problem statement. In problem statement, first is seismic weight of the structure. So if you don't know how to calculate the seismic weight of the structure, you can check our video, because there is no any change in calculation of the seismic weight. So W is equal to 37,489.24 kilonewton. Location is Patiala, which is under zone 5. Now building details. The building is 7-story reinforced concrete special movement resisting frame, that is SMRF, and the building is a hospital building. Then some details like size of column 0.3 by 0.6 meter, size of beam 0.23 by 0.45 meter, internal wall and external wall data is given, and we are assuming that RC frame building with brick infill panels. Okay, so these data will be required. This data will be required during the calculation. Okay, so let's start. Let's start our solution. So as per IS 1893 2025, design earthquake hazard. Okay, so there are two categories here. This category is applicable for us in this problem: design earthquake hazard, which is clause 6.2 IS 1893 2025 part 1, page number 16. So if you see there, there is a formula. Yes, 6.2 design earthquake hazard. Now the formula is given: VBDH is equal to AHD into W. Okay, so I have written same here. So you can see here VBDH is equal to AHD into W, where AHD is ZI ANHTH upon R. So this is our AHD. Okay, that is, what is AHD? Design horizontal acceleration coefficient of structure. W, we know that it is the seismic weight of the structure. Z is the earthquake zone factor. I is the importance factor, and ANH is normalized the horizontal spectral acceleration coefficient of the structure. Okay, so previously the formula for VB was AH into W, and AH was Z by 2 I by R and SA by G. So you can see there are some changes in the formula. So let's calculate. We have W. Okay, so we have to find Z, I, ANH, TH and R. So we need to calculate these four parameters. So to find the zone factor value of z, to find the value of z or the zone factor, uh, we need to refer table 1, which is related to the categories of the building, and this table is available in IS 1893 2025 part 5, page number 11. So if you go to this table, yes, so here you can see table 1, categories of the building. So in this table, the categories are given like special building, critical building, okay, then important building and normal building. Against that, they have given return periods in years, okay, and against that there is a description which building shall we call special building, okay. So you can see there are so many descriptions are given. So I will show you. Our building is hospital building, and we have assumed that, like, there are so many options like residential or commercial building with occupancy more than 100, okay, educational building, public building, and we have assumed here our hospital building that are not critical to the functioning of hospital in the aftermath of the earthquake. So we have assumed. You can check the type of building you are going to design, you can see and choose the category, okay. So this period is important, 975 for LSM, okay. So here you can see building category is important building. Second, return period is 975 years. And why it is important? Because we have selected this building, hospital building that are not critical to the functioning of hospital in after whatever it may be. Okay. Then you have to go to table 3. So this is how you select the zone. Previously the zone was entirely depend upon the location of the structure. Now it is correlated with the many things like type of structure or importance, category of the structure, then return period and all those things. Now you have to come back to IS 1893 part 1, page number 19, and there is a table 3, earthquake zone factor Z for different return period in different earthquake zones. So we will go to page number 19 here. So here you can see table 3. So in table 3, earthquake zones are given. As you can see, zones are now, one extra zone is there. Previously 2, 3, 4, 5 was there. Now 6th zone is added. Okay. So here you can see our zone is fifth zone, which is given in the problem. And the return period is 975 year. So we have to see this value 0.0400. Okay. So this is how you can find the zone factor. But okay, so earthquake zone 5, which is given in the table, or you can see the annexure also. Some cities are given and zone are assigned there. That's why this is how the zone factor come. This is the major change in IS 1893 2025. Next, so Z value is calculated. Now let's calculate the value of I, that is importance factor. Importance factor I of different buildings of 4 categories. So for that you have to go to part 5, page number 27. Okay. So you'll go to page number 27. Yes. Yes, here you can see table 6 importance factor I for I of different building of the four categories. Now our building is concrete building and we just find our category is important building. So if you see here, all has one value. Okay, importance factor I. So we'll select the I value which is equal to 1. Okay, but if you want to change importance factor, you can refer this clause 8.2.2. Okay, there is a provision also for importance factor you can take higher, but this clause you have to read 8.2.2, but right now we will not cover that part. Okay, now I value is 1. Now next, response, sorry, r value we are going to find. How to find r value? So for that, table 7 is there, elastic force reduction factor for building with different structural system, is 1893 part 5 page number 27. On same page you will get, so this is part 5. So here you can see table 7. Now in given data, it is mentioned clearly it is RC building with special moment resisting frame, design and detail as per IS 13920 part 5. So our R value will be 5. So our R value is 5. Now there is this is very important part of finding the time period. Okay, so as per clause 8.2.4.3 IS 1893 part 5 page number 31, approximate fundamental translation natural period TA. Okay, so I will show that formula. Yes, here you can see basically A, B and C options are there depending upon the type of building. So we are falling in this category, building with reinforced concrete, movement resisting frame with or without RC structural wall and with or without URM infills. So for this category, we have to refer this formula. For steel building, this is the formula B, and if the building is not following in any of A and B, then you can go for C. Okay. Now this is the very important formula. So TA is equal to, I have written this formula here. TA is equal to, that is the time period, 0.075 h raised to 0.75 divided by square root of 1 plus 0.2 rho cc plus, and there is so much stuff is given. Okay, now I will explain one by one. So this is very important. Here you can see this h is the height of the building. So the height of the building in our problem is 24.5 meter. Okay. Next is this value, structural plan density in percent of all concrete columns at the base of the building. Okay. So I'll just show you the plan. Just a minute. So this is the plan of the building. So 1, 2, 3, 4, 5, 6, 7. In one row there are 7 columns and 1, 2, 3, 4, 5. So there are 5 rows. Okay. So how to calculate structural plan density? So here you can see structural plan density percentage of all concrete column at the base of the building. So you will require the column size which is there 0.3 by 0.6. Okay, I have just told you how to calculate the, I have shown you total number of columns. So total number of columns are 35. Now, what is the total plan area? So if you see this plan, this is basically X direction. Plan is 24 meter, and in Y direction it is 16 meter. That means each bay the distance is 4 meter. 1 2 3 4 5 6 6 bays are there. 6 into 4 24 meter. In Y direction 1 2 3 4 bays are there. 4 into 4 16 meter. So what is the formula for the structural plan density? So this is the simple formula. Total area of the column at the base of the building divided by total plan area. Okay, so total area of column. So these are the number of columns, 35 at the base, and this is the size, cross section dimensions. So 35 into 0.3 into 0.6 divided by the total plan area, that is 24 by 16. So you just have seen, so this is 24 meter and this is 16 meter. Okay, so if you solve this, you will get the structural plan density 1.64%. Okay, now H is there, this value is we just calculated. Now this portion is related to the structural wall. Okay, so in our building there is no any structural wall, so I will skip this part. Okay, so it is not to be used in this problem, but this part is important, the last one. That means the structural plan density percent of masonry infill wall. This is structural wall and this is masonry wall. Okay, masonry wall alone at the base of the building in considered direction of shaking, where masonry infill wall are made with material whose density is more than 12 kilonewton per m cube. Okay, so same way you have to calculate. So I will show you. So this is the plan. So in this plan, in external as well as internal bays in X direction, there is a wall in each bay. So in problem it is given the center to center distance is 4 meter. Okay, you can see here. First we will calculate the length of wall. So length of wall. So I'll just draw here. 1 2 3 4 5 6 7. 7 bays are there. Sorry, 6 bays are there. 1 2 3 4 5. Okay, I think it's there are 6 bays. 1 2 3 4 5 6, and here 1 2 3 4 bays are there. So in this direction, this is the first bay, second bay, third and fourth. Okay, so here we will first calculate the earthquake is in X direction. So in X direction means in these bays we have there is a masonry wall. Okay, so we have to calculate the area of masonry wall. So masonry wall is present in all these bays. Okay, and this bay is consist of external wall, and this is also consist of external wall, and these they consist of internal wall. Okay, so it is simple mathematics, nothing complex. So I will just show you in X direction. This is the column orientation. So the columns are placed like this. Okay, and this center to center distance is 4 meter. So this center to center distance is 4 meter from this to this. So we will calculate the clear distance. Clear distance will be 4 minus 0.3 minus 0.3 means half of this and half of this. So we'll get this distance. Okay. So which is going to be 3.4 meter. Okay. And next, y direction we are not going to calculate in y direction. Similarly, you can calculate. So we know that length of wall in x direction. So 3.4 meter is in one bay. Okay. So external wall consists of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bays. In 12 bays, there is an external wall. So here you can see 6 in 1 into 2. Similarly, 3.4 is the length of the wall and 6 into 3. So in here you can see 1, 2, 3, 4, 5, 6. Internal wall 1, second and third. That's why into 3. So the 40.8 meter is the length of wall in external direction and 61.2 is the length of wall in internal, which consists of internal wall basically. So we'll multiply with 40.8 into 0.23 thickness of external wall plus 61.2 into thickness of internal wall. That means we are calculating this portion, length into width, this area. Okay. So, and that is 2 in x direction because we are calculating time period in x direction. So if you solve this, it comes out to be 16.42 meter square. To find the density, it is same total area of wall in x direction, which is 16.2 meter square divided by total plan area. We know that 24 by 16. So it comes up out to be 4.28%. 28%. Now we can calculate the time period. The formula is 0.075. This is h height of the structure raised to 0.75. This is the coefficient. Now this is 1 plus 0.2. We have calculated this value, and as there is no structural wall, this part is will skip or it will be 0, and put this value 1.64 here and 0.02 into 4.28. So just put the values and you will get the time period of the structure 0.695 seconds. Okay. Now using this time period, we have to find ANHTH. Okay. So we are assuming site class A. So you can go to page number 22. Page number 22, static analysis, equivalent static method, site class A and B. We have assumed this site class. So our time period is lying between 0.4 to 6. It is in between. So ANHTH, which is previously SA by G, now it is ANHTH, will be 1 upon TH. So the second category, site class A, B, and this second, our time period is ranging between this, so 1 upon TH. So 1 upon TH, we have find the time period. Just put the value, you will get ANH 1.44. Now it's done. VBDH, design base shear in horizontal direction. Z 0.4, importance factor is 1. ANHTH is 1.44. Response reduction factor is 5 and W is given. So if you can solve this, you will get the base shear 4318.73 kilonewton. So this is how you can calculate in x direction VBDH. Similarly, you can calculate in y direction. The change will be here. You have to consider the walls in y direction. Okay, for y direction you have to consider this area of the wall. So as per that, time period will change and your base shear will change. So it is almost 1.25, 1.2 to 1.4 times greater than what we have calculated using 2016. So it depends which zone is there, type of building, and that means, but one thing is sure, that base shear is going to increase. Okay, so I hope you have got the idea about 1893 2025 part 1 part 2. If you have any doubt, you can comment me. I will surely reply. Thank you. Thank you so much. Please like, share, subscribe the channel. Thank you. Thank you so much.